Hello and welcome to the Harvard Radcliffe Institute. My name is Claudia Rizzini. I'm the Executive Director of the Fellowship Program. The Institute is one of the world's leading centers for interdisciplinary exploration. We bring students, scholars, artists, and practitioners together to pursue curiosity-driven research, expand human understanding, and grapple with questions that demand insights from across disciplines. You can be a part of this vibrant community by attending public programs such as this one, visiting virtual exhibitions, or pursuing the special collections held at the Schlesinger Library. To learn more, you can visit radcliffe.harvard.edu and sign up to receive more information on news and events. We'll begin the program with a presentation by Alisa Bokulich. After the presentation, the speaker will respond to questions from the audience. Please use the Q&A feature on Zoom to submit your questions at any time throughout the program. We ask that you keep your questions brief to allow us to address as many as possible in the time that we have together. It is my pleasure to introduce Harvard Radcliffe Institute Fellow Alisa Bokulich. Professor Bokulich is a professor in the philosophy department at Boston University. Since 2010, she has served as the director of the Center for Philosophy and History of Science at Boston University, where she also organizes the Boston Colloquium for Philosophy of Science. Additionally, she is an associate member of the History of Science department at Harvard University. Professor Bokulich's research focuses on scientific modeling, data, and explanation in the physical sciences, and more recently, in the earth sciences. She has published on a variety of topics, including history of physics, inter-theory relations, thought experiments, supertasks, fictions in science, metaphysical interdeterminacy, non-causal explanations, data models, and modeling in the geosciences. The author of Re-examining the Quantum Classical Relation Beyond Reductionism and Pluralism, Professor Bokulich interlaces reflections from the history of science, philosophy of science, and contemporary physics, and details a new way of considering inter-theory relations in scientific exploration. Throughout the book, she expresses original and insightful alternative ideas on how we should conceive the relation between classical physics and quantum physics. She is the co-editor of 4 additional volumes. At Radcliffe, Professor Bokulich is working on a book project entitled Philosophy of Geosciences, Data, Models, and Uncertainty. Despite being largely neglected by philosophers of science, the geosciences have the potential to enhance understanding of scientific methodology and the intricate interplay between data and models. Professor Bokulich's aim is to address this gap in the literature by studying the philosophy of geosciences, centering issues of data, models, and uncertainty. The geosciences confront some of the most pressing global issues today, including climate change. The book will demonstrate how geoscientists develop dependable knowledge about a complex world despite the uncertainties that arise in the data they gather, the models they create, and even the uncertainty estimates they give. Professor Bokulich earned her PhD in History and Philosophy of Science from the University of Notre Dame. She was the first woman ever to be tenured in the philosophy department at Boston University, and the first woman to become the director of the Center for History and Philosophy of Science in North America. And now it is my pleasure to give the virtual floor to Alisa Bokulich.
Thank you so much, Claudia, for that wonderful introduction. And I want to express my deep gratitude to the Radcliffe Institute for the support and the time to carry out this research project. I'd like to thank my wonderful community of fellows for providing such a stimulating environment in which to do this research. And I want to thank all of you for joining us today to talk about this topic of measuring the Earth, C.S. Peirce, uncertainty, and the pragmatic philosophy. I'd also like to acknowledge that we are working on the lands of the Massachusetts people, and their continuing work protecting our lands, educating us about harmful stereotypes and racist school mascots and our state flag and so forth. So there's much work for us to do together. So thank you everyone for joining us. I'm sorry that we can't be together in person, but I'm happy that at least we're able to welcome you from far and wide around the world to talk about C.S. Peirce. So let me just introduce Peirce. I'll quickly explain who he was. I'll give a brief introduction to what is geodesy and a selective history. I'll talk about Peirce's work as a geodesist, and then how his work as a geodesist influenced his pragmatic philosophy. I'll conclude with looking at how the continuing relevance of his program for geodesy today, and draw some broader philosophical conclusions. The thesis I want to argue today is that Peirce's work as a geodesist and a metrologist is a critical but unappreciated source of his pragmatic philosophy, and his pragmatism continues to hold valuable lessons for thinking about the nature of science and scientific uncertainty today. So let's get started. So Charles Sanders Peirce was born in 1839. He, in fact, grew up just here across the street from the Radcliffe Institute. You can see in the bottom left his childhood home. And if you walk past that home, if you're here in the area, you can see this plaque dedicated to Peirce. It's also interesting that he graduated from Harvard in 1859. And shortly after graduating, he actually lectured at Elizabeth Agassiz's School for Girls. This School for Girls was first run out of her living room, and it then became the Harvard Annex, which then developed into Radcliffe College. So Peirce was helping to educate women about the nature of science when they weren't allowed to be students at Harvard University. And so there's a nice connection to our venue today. So if you look at the manuscript image there at the bottom, these are views of chemistry sketched for young ladies, which I found here in the archives, that talks about how Peirce was teaching at the Radcliffe essentially before the Radcliffe became a full-fledged college with Agassiz as its first president. The Peirce papers are here at Houghton Library. So I've been spending a lot of my fellowship time here. You can see a picture of the beautiful reading room at Houghton Library. 74 linear feet archive, so there's a lot of material to be working through, and I've really been enjoying the opportunity to get to know Peirce on a more intimate level by looking at his writing, and both published and unpublished. So Peirce's biographer, Max Fish, gives a somewhat over-the-top introduction to Peirce. He says he was the most original, the most versatile intellect that the Americas have thus far produced. But he also gives a sense of how Peirce was really a polymath. He made contributions to mathematics, to astronomy, to chemistry, to geodesy, surveying, cartography, metrology, spectroscopy, engineering. He was an inventor, a psychologist, a philologist, a lexicographer, historian of science, mathematical economist, dramatist, actor, short story writer. The list goes on and on. But what Peirce is best known for today is his work as a philosopher, and in particular, his work founding a school of philosophy known as pragmatism. This pragmatic philosophy that he established was then developed by many other thinkers, such as William James and John Dewey. He thought that it didn't get developed in the way he wanted, so he often called his philosophical school pragmaticism, which he said was an ugly enough name, no one would kidnap it. So, but I will use the term pragmatism as the name of his philosophy, nonetheless. Okay, so what is geodesy? So geodesy is the science of accurately measuring and understanding Earth's geometric shape, its orientation in space, and its gravity field. Geodesy is fundamental to mapping, navigation, and engineering, in addition to the basic scientific question of what is the figure of the Earth, to use the historical term. Although we tend to think of the Earth today as this perfect sphere, because it is rotating on its axis, the Earth actually bulges around its equator, giving the shape of an ellipsoid. So on the left side, the slide here, you see the ellipsoid of the Earth with its bulging center. But this ellipsoid also is an idealization of sorts. And the Earth is in fact a much more convoluted geoid, which is the shape on your right here, this colorful diagram. Now, this has been slightly exaggerated in the vertical elevation to be able to show you its surface features, but this geoid is the shape that an ocean surface, the Earth is covered in 70% of the ocean. If we imagine it completely covered, the geoid is the shape that the ocean surface would take under the forces of gravity and Earth's rotation alone, which results from uneven distribution of mass on the Earth. And it's very difficult to determine what the shape is. It requires lots of gravity measurements, surveying, calculations, and so forth. And I think, as you see, it's a really lopsided, convoluted thing. And how do we come to know that shape? How do we come to know the figure of the Earth? Well, there's a long history behind this. We don't have time to do the full history, so I'm just going to jump in a few highlights. One key landmark was the work of Jean Richet in 1672. He traveled to the equatorial island of Cayenne in French Guiana, and he noticed that a pendulum clock swung more slowly there in Cayenne than in Paris, in fact, losing 2 minutes and 28 seconds a day. Or equivalently, that the length of the pendulum that beats exactly 1 second in Cayenne was shorter than the length of a pendulum in Paris. This was the beginning of the science of gravimetry. We have a picture of Richet here in his an engraving depicting Richet with his pendulum clock in the background and his various surveying instruments. And on the right, you see the image of the pendulum clocks in Paris versus in Cayenne, which is close to the equator. Now, Isaac Newton, who is well known for writing the Principia, which introduced the laws of mechanics and universal theory of gravitation, was excited by Richet's experiments and his observations. And he explained this result by showing that it was a result of his theory of gravity and the rotation of the Earth. And so the Earth has this oblate spheroid shape, that is squashed ball, if you will. And in his Principia, he gives this table that I've depicted, shown here, that shows how those gravity measurements should change as you change latitude. He also showed how arc measurements, length measurements, would change with latitude. And this was in support of the oblate shape of the Earth. However, there was another sort of program of measurement that was happening around this time, building on the work of Jean Picard's measurement of the length of 1 degree meridian arc around Paris. The Cassini family, which is the father Giovanni Cassini and his sons, carried out various measurements of the length of 1 degree around Paris, and noticed that the length of the arc through various surveying techniques and triangulation turned out to be longer than the length of a degree north of Paris. So if you can see we have these two potential shapes of the Earth, the oblate spheroid, which was what Newton's theory predicted and Richet's pendulum gravity experiments supported. And on the other hand, there was this arc meridian measurements by the Cassinis that suggested at least that Earth was a prolate spheroid, that it was longer and narrower around the equator. So we had these two competing theories of the shape of the Earth at this time. And in order to settle this dispute, the French Academy launched several geodetic expeditions around the world. This map should look familiar to the Radcliffe Fellows who went on our field trip to the Harvard Map Collection at Pusey Library. This was one of the maps that the wonderful librarian David Weimer pulled out for us to look at, so hopefully you recognize that. And this beautiful map in the Harvard collection shows in the top left the arc measurements, triangulation arc measurements that were made by Maupertuis and Clairaut in 1736 up in Lapland or near the polar circle. Right below it, you see Picard's earlier measurements of the arc meridian in Paris. And in the large center map, you see the triangulation networks of Bouget and Condamines and Godin's arc measurements in Peru, which were then Peru, today's Ecuador. And the far right is the arc measurements in South Africa. So what we see in this map is this attempt to resolve this dispute about what is the shape or the figure of the Earth. And these more extensive geodetic surveys established that, in fact, Newton was correct, and that it is an oblate, not prolate spheroid. So once it was determined that, in fact, this Earth is this oblate spheroid, it has polar flattening, this squishing of the Earth's shape, the central problem of geodesy was then to quantitatively determine the degree of polar flattening. How squashed is this Earth ball? And we have this very simple equation to describe this flattening. And there were two different measurements, which I've already introduced. One set of measurements was measuring the strength of gravity using pendulums. And the other approach was measuring differences in the length of a meridian arc with various latitudes through triangulation networks and using theodolites and survey techniques. And these two measurements did not agree for a very long time, which is something that often happens in science. We have these ways of making measurements, but how do we correct for the measurements? How do we improve the quality of our measurements? How do we bring these various different approaches into agreement with each other? And this is a wonderful diagram here by the scientist, earth scientist, or geoscientist Hoarth, who shows that if you plot what the values of the flattening are, we have the true value around 298. And we see that the light gray circles are the measurements of polar flattening due to the arc length measurements. And the black circles are the measurements of flattening due to gravity measurements using pendulum. And so what we see here is there's this scatter of these different results, but over time, they eventually, long enough, seem to be finally converging and agreeing in their value. And it's interesting to look at this progression over time and how scientists were able to accomplish this, bringing these two modes of measurement into agreement with one another. And it was in this trying to bring these two different modes of measurement into agreement and improving the precision and accuracy of pendulum gravity measurements that we find Charles Sanders Peirce. So, although Peirce is often thought of today simply as a philosopher who introduced the pragmatic philosophy, in fact, his day job was as a geodesist. So in 1807, Congress under President Jefferson establishes the US Coast and Geodetic Survey. This is the first scientific agency in the US. So this geodesy really played a very important role around the world and here in the US in establishing science in the US, and yet many of us never learn about geodesy. So it's fun to think about how important this history is. Peirce graduates from Harvard in 1859, as I said, and he becomes a temporary aide in the Coast Survey. He's promoted then to assistant of the Coast Survey in 1867. And part of his job working for this US scientific agency is to travel around the world and coordinate with scientists all over the world and to compare the measurements that he's doing here with their measurements there, his instruments with their instruments, trying to improve the precision and accuracy of these gravity measurements. He makes, in 1875, his second Coast Survey assignment in Europe. He's invited to give a presentation. This makes him the first American scientist at a meeting of an international scientific organization. So Peirce here, again, trailblazing in the history of science in the US. So he works on various ways of improving this. He, for example, works in metrology, looking at how to define the meter and how to make sure that the meter measurements are precise and accurate. He actually suggests that that it should be tied to a wavelength of light. I can talk about that later. I won't have time today. But he also has designed and built for Peirce pendulums. They're called Peirce pendulums today. Obviously, he didn't call them that, but trying to think about how to improve the precision and accuracy of these measurements. So he was really involved in geodesy and in gravimetry. So he also did a number of things related to weights and measures, which I can come back to later. And finally, he's forced to resign in 1891. And in 1914, as I just discovered recently in the Peirce archives here at Houghton Library, he was actually continuing to work on a manuscript on the figure of the Earth, even on his deathbed, just in the months leading up to when he passed away in April of 1914. So I hope you see from this list, even though I went through very quickly, that geodesy was a central part of Peirce's life. It was something that he did for over 50 years, and he was really invested in thinking about work as a scientist. And my argument is that that has shaped his pragmatic philosophy in ways that we haven't recognized. Okay, so let's try to look at how his work in geodesy could have influenced his pragmatism. So in one of his Coast Survey reports, he writes, "The value of gravity determinations depends on their being bound together, each with others. At the meeting of the International Geodetic Congress in Paris, which is one of the first international scientific organizations, geodesy again at the forefront of the internationalization of science, in 1875, it was resolved at the suggestion of the writer, that is Peirce himself, that the different states should carry their pendulums to Berlin and swing them at the Eichungsamt there. This has been done by Switzerland and Austria and will be done hereafter by every survey which is not willing to sacrifice the solution of a great problem based on national exclusiveness. And this is the key point he writes here: geodesy is the one science, the successful prosecution of which absolutely depends on international solidarity, right? So he really has this conception of science as requiring this kind of international cooperation and solidarity. And it was this geodetic work, I think, that influenced the development of Peirce's social theory of epistemology. So here he writes in The Fixation of Belief, one of his famous essays, the problem becomes how to fix belief, not in the individual merely, but in the community, right? So we think about scientific knowledge not being attached to any individual scientist, but as being a part of this whole community investigating together. In another manuscript, he writes, the scientific world is like a colony of insects, and that individual strives to produce that which he himself cannot hope to enjoy. One generation collects the premises in order that a distant generation may discover what they mean. So again, it's this collective endeavor of science that's important, and that's what makes it succeed. And I'll just mention this little doodle here. Peirce was a very prolific doodler. And as you work through his archive papers, all over the margins of his various manuscript drafts, you see these wonderful little pictures. So I thought I would just include one here to give you a sense. Another key part of his work in geodesy that I think influenced his pragmatic philosophy is this recognition that gravity measurements are imperfect, that gravity measurements require correction. So he spent a lot of time trying to discover what are the various corrections of the data that he's collecting and the various sources of error or biases or corruptions of the data in various ways. And so he has this long list that he develops of these corrections for his measurements. And I think here we see this important idea that the data is the result of an imperfect human measurement, right? And that good data often requires reduction. This is central to geodesy. It requires processing, correction of raw data measurements to correct for various biases and errors. And I think it was his work as a geodesist that really sort of helped him recognize that. I think it's an important lesson for today as well. He also has this idea of science being this self-correcting enterprise. He says induction is the experimental testing of a theory. The justification is that although any conclusion at one stage may be more or less erroneous, yet the further application of the same method must correct the error. So again, this idea of science as this process continually undergoing correction. He also has this wonderful quote, dealing as they do with matters of measurement, scientists it is, they hardly conceive it possible that absolute truth should ever be reached. Therefore, instead of asking whether a proposition is true or false, they ask how great the error. And again, I think this is a key part of his pragmatic philosophy. We don't need to know, is it perfectly true or false? How great is the error? What can we do given that amount of error as far as our practical actions? Again, Peirce sees science as a process rather than a set of facts. He says if we were to define science in the sense of characterizing it as a living historic entity, and again, I think this is important. We don't tend to think of science that way. It's a living historic entity. It has a history that's important to know for understanding where it is today. And it's living, it's evolving, it's continually changing. So he goes on, we should think of it as this living historic entity, that we shouldn't think of it simply as some body of organized knowledge. Instead, Peirce emphasizes we should think of it as a diligent inquiry into truth for truth's sake. We may never achieve that fully, but it's this process of knowing for its own sake that characterizes science. Again, another passage, he says, your problems would be greatly simplified. Instead of saying that you want to know the truth, you were to simply say that you want to attain a state of belief unassailable by doubt, okay? How much do you doubt? How important is that doubt? That's what's fundamental. He says, again, we hope that in the progress of science, error will indefinitely diminish, just as the error of the value of pi, 3.14159, the value given for pi will indefinitely diminish as the calculation is carried to more places of decimals. What we call pi is an ideal limit to which no numerical expression can be perfectly true. And again, so this sort of provides a metaphor for his thinking about science, right? That we're trying to sort of reach this limit, but we're always sort of working at improving it along the way. Now, other key elements of his pragmatic philosophy that I think we can see coming out of his work in geodesy is fallibilism. So Peirce is actually the one who coined the term fallibilism. So if you've heard of the term fallibilism before, fallibilism is the doctrine that our knowledge is never absolute, but always swims, as it were, in a continuum of uncertainty and indeterminacy. So here, this idea is we have to recognize that science is fallible, that knowledge is fallible, that we are engaged in this process of trying to understand. We're always dealing and managing various levels of uncertainty. Another wonderful metaphor he gives in another passage is science is, quote, not standing on the bedrock of fact, it is walking upon a bog. And it can only say that this ground seems to hold for the present. Here I will stay until it begins to give way, unquote. Now, even though he's a fallibilist, the sort of critical of our ability to come to know the absolute truth and perfect accurately our knowledge, that this fallibilism, that we should always be ready to change our beliefs in light of new evidence, that we should always sort of recognize that we're engaged in this project in real time. He balances this fallibilism with what he calls critical common sensism. He says, quote, it would be a waste of time to adjust my feeling of doubt more accurately, since neither would have nor ought to have any effect upon my scientific conduct. Again, this idea of action and agency in practice. Instead of wasting my effort, I devote my energies to learning more about the subjects concerning which I have any considerable doubts. With small doubts, I neglect until I can reduce the amount of my doubt concerning subjects of greater importance. So again, even though he was a fallibilist, right, that recognized that we could come to know that any piece of our knowledge is erroneous, is wrong, at the same time, he thought that shouldn't lead to this kind of skepticism where we doubt everything. He says we can't function if we doubt everything. We have to sort of take for granted a certain body of beliefs as we go forward, with the willingness to update as we get more information. So I think this image I showed you earlier, right, of the arc measurements and the gravity measurements and how they didn't agree initially, but how they eventually converged over a long period of time on this value, gives a nice sense of this idea of Peirce's of the truth as sort of the limit of the end of inquiry. It's this point off that serves as a goal that scientists are working for, even though they may never fully achieve. It's something that describes how we improve as we go over time. So he says, the perpetual recognition of errors in geodetic data and need to improve instruments and data manage those errors undergirds his fallibilism. The iterative process of trying to refine the figure of the Earth provides a nice model for how we can be realist. The Earth has a definite shape, with the recognition that our current measurements and conclusions of that shape are fallible. He writes, quote, inquiry properly carried on will reach some definite or fixed result or approximate indefinitely towards the limit. Again, another passage, the method of science, which communally seeks to conform beliefs to that which is independent of them and has as key enabling hypotheses that there are real things whose characters are entirely independent of our opinions about them. Any man, if he has sufficient experience and reason enough, will be led. Okay, so again, we have see this connection between his work in geodesy and his pragmatic philosophy. So what about today? So coming back to geodesy today, I think we can see that Peirce's program of continually trying to improve the measurements of the figure of the Earth, recognizing that our current understanding of science is fallible, that it's something that needs to be improved over time, is still very relevant today. And in fact, we are on the threshold of having a new geoid introduced, the new geopotential datum of 2022. A geodetic datum is an abstract coordinate system with a reference surface, such as sea level, that serves to provide known locations to begin surveys and to create maps. And this new reference frame and geoid model are continuing this program of the iterative improvement of the figure of the Earth. Now, one of the issues is that these older surveys were based on these physical artifacts, these geodetic markers. So at the bottom center, you see a geodetic marker that you could still see today at the old State House that was placed by the US Coast and Geodetic Survey that Peirce worked for. On the right is another marker, physical marker, that was placed in honor of Peirce at Indiana University, Purdue University in Indianapolis University. And what you see on these maps is how the new geopotential datum of 2022 is going to revise that geoid again. So the center of the Earth is going to move by about 2 meters. Again, that's a very high level of precision, but it's something that's become important in the age of GPS data. We'll also see that the vertical heights that maps, like, are you above sea level? Is your home going to flood and so forth? These are going to be revised with the new geopotential datum of 2022. The vertical can change by as much as 1 meter. And the horizontal can change by as much as 3 meters. So those two maps of the states give a sense of what sort of changes are about to happen in this geopotential datum and what implications they'll have for future mapping and so forth. So the conclusions that I would like to draw here is the following: that Peirce, his work as a geodesist, deeply influenced the development of his pragmatic philosophy, and that pragmatic philosophy has continuing relevance for our work, our philosophical work, our scientific work today. So the first key to summarize his social epistemology. The strength and epistemic authority of science lies in its communal nature. The international solidarity of science, global cooperation, is essential to the success of science. I think we see that in Peirce's work as a geodesist, as his encouraging scientists from around the world to come together to compare their pendulum measurements, to work together to determine what the figure of the Earth is. This social epistemology of science being this international global endeavor that requires this cooperation is something that originates, that has its wellspring in this geodetic work that Peirce contributed to. Today, we would say the social epistemology is sort of iteratively improved, that it is also by having a diversity of people involved in science from around the world that allows the various errors and biases of certain national sciences to be weeded out. And so this social epistemology, I think, is a really key idea that we see in Peirce's early work based on his geodetic work, but yet has a continuing relevance today. Second, I think there's important lessons for thinking about the philosophy of data. We are in the age of big data. There's a new data science building going up, for example, at Boston University. There's a lot of buzz about data. What we see with Peirce is this recognition that data is the result of a measurement, a human-made measurement. It is imperfect. That data cannot be equated with the world. That data gives us insight to the world, is tied to the world, but we have to look out for possible sources of error in our data. So this idea of data being something that requires processing, correction, modeling the sources of error, always looking for new sources of error, figuring out ways to correct for it, is what's required in order for data to become useful as evidence in science. And I think it's important that we have that more sophisticated understanding of the nature of data as we go forward. Third, fallibilism. Knowledge is never absolute, but involves varying degrees of uncertainty. This is not cause for skepticism, but rather Peirce's critical common sensism. What is critical common sensism? As we saw, he says, don't manufacture doubt, prioritize questions, assess the implications for action. Action does not require certainty or proof. Again, important lessons, right? Sometimes people think, if there's any doubt whatsoever about climate change, we just wait to have all the answers. And Peirce very early on was arguing, no, that's nonsense, right? We need to act always, there's always going to be some doubt, but we need to act in the face of that doubt, and we need to prioritize that doubt. There's no point manufacturing doubt unnecessarily. And so that critical common sensism, I think, is also an important lesson. Should we be wearing masks? Yes, of course. Is there any doubt? Don't worry about it, right? This is something we know enough about to guide our action. We also see this key idea of science as an iterative process, that science is not some fixed body of fact. The refining of science as new evidence comes in is not a failure of science, but it's how science succeeds. So this idea that we often tend to think, well, scientists are changing their mind. We've seen this in the pandemic. They're updating, they're revising their views. That is how science works. That's why science succeeds. This is not a failure of science. That continually updating, reassessing our fallible beliefs is what allows science to be as successful as it is today. So genuine uncertainty, in some sense, is what propels science forward. So he had this idea of thinking of uncertainty in this positive way and not as a negative way. That we don't want uncertainty to block the way of inquiry. We want uncertainty to propel us forward. And that this iterative process of science, I think, is an important lesson that has implications for science education today, for example. So finally, I hope I have convinced you of my thesis argument here, which is that Peirce's work as a geodesist and metrologist is a critical but unappreciated source of his pragmatic philosophy, and that his pragmatism continues to hold valuable lessons for thinking about the nature of science and scientific uncertainty today. Thank you very much.
Thank you, Alisa. Absolutely wonderfully fascinating talk. And there are lots of questions. So let me get to the first one. And the listener reiterate what I says. Thank you for the fascinating talk, exclamation mark. The quest for accuracy in the figure of the Earth is totally intriguing. But can you also say a word about why such precision matters? What are the implications?
Good. Okay. So if you think about why are we doing this updating of the 2022 datum, right? We saw that these are going to be influencing where sea level is, what houses and buildings are in floodplains. It's going to be important for launching satellites. We need to understand the shape of the Earth and its gravity fields, because science and engineering have progressed to a point where this level of precision is important. So I think having accurate maps that line up, maps that are consistent and that agree, is part of getting this more accurate measure of the figure of the Earth. And so it's something that's important sort of for practical reasons, as well as being important for fundamental research, basic research of understanding what the figure of the Earth is. Thank you for that question.
Yeah, and the next one, does Peirce ever mention the legacy of Sir Francis Bacon? I wonder, because Bacon held that science was fallible, but that we achieved stages of certainty and then corrected errors rather than give into skepticism.
Yes, so he does. And certainly Bacon is part of this empiricist tradition that I think can be characterizing of Peirce's work also. So Bacon has this wonderful view that the scientist is not like the spider who spins webs out of themselves with no input from the world. They're not like the ant either, that merely collects things as they are, but rather he says the scientist is like the bee that gathers pollen from the field and transforms it into honey. And this Baconian idea, I think we see in Peirce's idea that we need to, as scientists, we gather information, we gather empirical data, but we don't take it at face value. So he's a more sophisticated, I think, empiricist, and that he recognizes data needs to be corrected and transformed in various ways. And I think these insights can be traced back to many other figures as well, but they have this nice form in Peirce's pragmatism and fallibilism.
Absolutely. On the issue of uncertainty, this listener says, I have read that Peirce believed in a fundamental uncertainty that was not simply the result of error-prone measurements or technical shortcomings. Can you expand on that set of ideas, especially as you mentioned in science education?
Right, good. So I think there's many different sources of uncertainty, right? We can think about uncertainty in measurement. We can think about uncertainty in our theoretical knowledge. And we can think about some of the uncertainty in the world itself. And I think there's this third sense of uncertainty or third source of uncertainty that might be even more difficult to understand. And it might be related, I think, to some of Peirce's evolutionary ideas, but the Earth itself is this dynamic thing that's always changing, that we have tectonic uplift, we have subsiding in some places, we have isostatic readjustments. The Earth itself is something that's continually changing. And so there's a kind of uncertainty that we may not be able to fully resolve, in that things are continually changing, right? We're like stepping into a river that continues to flow. It's not the same water all the time. And so I think that idea that the world itself is changing can be thought of as another source of uncertainty, apart from just our imperfect measurements and our imperfect theoretical knowledge. As far as science education, that's a good question. I mean, I think one of the most important things is that we can do a better job of communicating as science educators about the excitement of the inquiry, about science as a process. It's not memorizing a set of facts that are sterile and locked in stone, but as this pursuit of inquiry, about this desire to try to understand things better, and that there can be disagreements in science, right? We saw the arc measurements versus the pendulum measurements, that we think of science as this dynamic community working together to pursue these questions. And how would that maybe influence how we teach science? that we teach science as having a history that can have various sources of bias. For example, the history of sexism and racism have influenced science. If we see that science is this human endeavor where we work together to sort of recognize these sources of error and bias and then try to correct for them over time as a community, that could get more people excited about science than just thinking of it as a storehouse of facts that we have to memorize. And so I think there are a lot of implications for thinking about how we teach science, but also I think there are these broader implications for the public understanding of science, right? I think in the case of this, this pandemic that we're still unfortunately in, there's kind of been some frustration by people that they wanted these final facts from science. They wanted all the truth and answers up front. And what we recognize, I think if we taught science differently, we would recognize that the pandemic is a forefront, a cutting edge scientific process of inquiry. And that as the epidemiologists and the virologists are getting more information, they have to revise their views. And that if the public understood science as this process of inquiry, that might help us sort of appreciate and learn to trust science as a process rather than expect these absolute answers that never change. Thank you for that question.
Yeah, talking about this ever-changing nature of science, the listener says, do you also, I'm used to thinking of science as a living, changing thing. Do you also think of philosophical schools as living, changing things specifically? Do you, to your work, are there ways that you update pragmatism in light of what you just said?
Absolutely, a wonderful question. Yes, and so I actually think that philosophy and science are, I mean, historically they were one and the same. Science used to be called natural philosophy, and Whewell actually introduced quite late the term scientist. And so it's only quite recently that philosophy and science have become separate from one another. And we can think of philosophy as engaged in this sort of pursuit of truth in the same way that Peirce describes science as this pursuit of truth. And I think that philosophy, people often say, oh, philosophy doesn't make progress, but I think it does. And I could give an example that I mentioned in the talk is this view of social epistemology. This idea that science requires this community of knowers and that we get better knowledge through this community. And I think in philosophy, we're starting to recognize the importance of understanding philosophies from all over the world. We're understanding the importance of what's required for this community of inquirers to have more adequate views. So I think we do update this. And I think my own work, for example, has been looking at data recently and thinking about how our understanding of data needs to be improved over time and how it is that we shouldn't think of data and models and theory as these two opposite things, but they work together. And again, I can see some antecedents of that in Peirce's work, but I think there's a lot of interesting work thinking about the nature of data today and biases and errors in data and how that needs to be corrected. And so I'm working as a philosopher of science. I'm not a pragmatic philosopher full stop, but I'm looking at pragmatism's relevance for the philosophy of science. And so drawing those two together. Thank you for that question.
I'm going to join a few questions together here. Much of science depends on models, weather, climate, environment. One problem here is of accidental or unforeseen events. Can you comment on these? And also, another listener asked if there are progress made in how we make, how we can measure uncertainty. So if you can talk about both things.
Good, yes. So I think, as far as progress and uncertainty, I think as we see in Peirce, I keep going back to Peirce, he was continually looking for new sources of error, right? He was continually looking at how do I identify sources of error, and then how do I model those sources of error? How do I measure the influence of those sources of error on my results? And so I think we've gotten a lot better at that process of identifying sources of error in our knowledge along the way and how to model those effects. And there's all sorts of sophisticated statistical methods that have been developed to deal with uncertainty and error and so forth. So I think it's something that we are getting better at over time. As far as models and the changing world, again, I think come back to this Peircean idea of science as a process, of the inquiry of knowledge as a process. We build these idealized models, often as a heuristic initially. It makes all sorts of false or idealized assumptions, what I've sometimes said, fictional assumptions, that we imagine the Earth to have all its mass concentrated at a single point, or point particle that has no dimension. These idealizations of physics obviously don't exist. There are no frictionless planes. There are no perfect simple pendula. These are idealizations that allow us to sort of bring certain mathematical machinery to bear on our inquiry of the world. But as our inquiry proceeds and becomes more sophisticated, we need to revise these models in various ways. We need to think about how to adapt and improve these models in light of our projects and our inquiry. And so I think you're absolutely right that we should be thinking of model building as itself a kind of extended research program, where we often begin with a simple model and complicate it in various ways. And of course, there's all sorts of interesting philosophical questions about what's the appropriate level of detail or idealization given the particular project of your inquiry. And so I've done some work looking at idealized models and what level of idealization is appropriate for different sorts of projects. So there's lots of interesting work in the philosophy of science on scientific modeling and those questions.
That's great. One aspect of uncertainty concerns its historical development and unfolding. What ancient references or texts does Peirce point to which aided him in the cultivation of his thought? Where does the conception of error or uncertainty originate for him?
That's a good question. So I've not gone through the 100,000 pages of Peirce's archives yet. This is an ongoing project. I'm just beginning to get to know Peirce with this Radcliffe fellowship. It wasn't an area of my research prior to this fellowship. And so I'm still just sort of discovering these questions. What I do see is that his thinking about uncertainty is related to his scientific work. And I think for him, that's more important than sort of thinking, there's some philosopher in the past that thought about uncertainty, that thought about error. There may be elements of that in his work that I haven't come across yet, but I think it's his work as a practicing scientist who is doing measurement, high precision measurement, and trying to think about that really forced him to develop these philosophical views about uncertainty and error. And so rather than sort of tracing his philosophy back to other thinkers, which may or may not be the case, I would trace it back to his work as a practicing scientist. We don't often think about Peirce as a scientist, but he was. That was his day job. He spent, and it wasn't just geodesy, he worked in experimental psychology, he worked in many different areas. And I think it was that practice of actually trying to do measurement and manage uncertainty and manage error that really shaped his philosophical thinking on this. But I think, yeah, there are interesting work to do to think about the history of uncertainty and the history of error. So that's a project to engage next.
Yeah, so I'm going to ask you a question about the use of metaphors by Peirce, and then we'll get to contemporary applications of his thinking. So the question about metaphors, Peirce uses quite a bit of metaphors in his scientific work, as well as his philosophical work. How important is metaphor in the conceiving of pragmatism?
This is a great question. So I think metaphor was very important for him. And he often talked about this also in terms of analogy, right? So you can think of a metaphor as being kind of an analogous context in which the insights that we get in this analogous context might inform this other context, or what we're doing there is a metaphor for what we're doing here. And so Peirce was a very creative thinker who was thinking about analogies. And I think we often don't think about science as using metaphor and analogy, but there is this creative element in science, right? How do you make progress on a new question that you haven't investigated before, or that other people haven't investigated adequately before? Oftentimes you do that by trying to figure out a way in which your present situation is analogous to some other situation. So if you look at many of the great scientists, so James Clerk Maxwell, for example, who discovered electromagnetism, the laws. He was very much trying to develop his theories of electromagnetism by thinking of electricity and magnetism as analogous to the flowing of water and how water flows through tubes. So he was thinking about hydrodynamics and the mathematics of hydrodynamics as an inspiration for his thinking about electromagnetism. And so this analogy transfer, this thinking of these metaphors or these analogs in these different contexts is an important source of how science progresses. You figure out where it's similar. So there's a wonderful philosopher of science by the name of Mary Hesse. And she talked about there's a positive analogy, things that you know that are analogous. There's a negative analogy. There's things you know are not analogous. And then there's this neutral analogy where you don't yet know whether it's analogous. And so I think this sort of work of analogy was important and metaphor was important for Peirce. He's often thought of his empiricism, people often thought he was sort of anti-metaphysics, but that's not true. He actually thought that metaphysics itself could be an important source of thinking about how to make progress in a particular area. And so thinking about unobservables, right? Which the logical empiricists, for example, were often critical of. Peirce thought, no, this actually plays an important role, these metaphors. Do we think of the atom as a little solar system? How does that metaphor help us make progress in science? So I think it's absolutely the case that this is beyond Peirce. This idea of metaphor analogies are an important wellspring of the creativity of science and the development of new theories and ideas.
Regarding the concept of social epistemology, that the strength and authority of science relies on community acceptance. Is the strength and authority of science diluted today with growing distrust of science among the general public? The lack of understanding of the iterative nature of science may play a role here. How do we build or rebuild the authority of science in society? Excellent question. Good. And again, I think there's sort of two different camps we want to think about when we try to tackle this question. On the one hand, there's what we might call the disinformation camp. There's some people who question science, not because they actually question it or don't understand it, but for politically motivated reasons, right? They are involved in disinformation, trying to raise questions, challenge, undermine science because it's for their economic self-interest or political self-interest. So that's disinformation. I think tackling that problem is going to require a different set of tools. Then the other hand, which is misinformation, which is people who perhaps genuinely are trying to understand the right way to think about things, but have gotten wrong information. How do we manage misinformation? And so when we talk about how to improve trust in science, I think that's the camp that we want to sort of be focusing on. How do we limit the spread of misinformation? How do we educate people about science as a process of inquiry? And what's interesting is that I think, we've been focused on teaching science as these facts, but there's been a lot of really good psychological research and cognitive science research that shows that simply trying to address trust in science through what's called the deficit model, right? That if we just explain more science to people, they'll come to trust it and believe it. Shows that research, psychological research has shown that's not the right approach. That we can't just keep giving people more facts and hope that eventually they'll come to believe and trust science. Instead, I think the approach, and again, there's some interesting new psychological research by Diana Skolnik-Weisberg on this, that shows if we teach people about how science works, about the process of science, about how we have this cross-check system, how we have peer review, how we have these coming to conferences to critically engage and debate things, that learning the process of science and what we would call the philosophy of science actually can do a better job of helping people come to learn to understand and trust science. And so on this question, I would recommend Naomi Oreskes' book, Why Trust Science? She talks about how science, again, she draws on these sort of Peircean ideas of science as this community, as this social epistemology project, and that if we learn about that project, that's going to help us learn to trust scientific expertise better. So I think there's a lot of echoes of Peirce, I think, in contemporary thinking about how to address that problem. Right. You kind of touched on this, but I guess this is not a new problem, and it was a problem in Peirce's time. And I wonder whether he had anything, this listener wonder whether there was anything specific that he said about this problem.
I'm sorry, which problem?
About, mistrust in science.
Mistrust in science, yeah. I think he wasn't, I mean, obviously this is something that's very much on our mind today, right? With climate denialism, denialism about evolution, how few people accept evolution is shocking still even to this day. We really have this problem that we're confronting with how to sort of change people's thinking about this, and when to trust science, when not to trust science. There's a lot of different contexts here that are important. I think that Peirce was not as sort of concerned with that question early on. I think he was concerned with the reliability of scientific knowledge, but he wasn't necessarily dealing with misinformation in the same way. But I think his philosophical work has many lessons for thinking about how to address those misunderstandings. And so I think he's somebody who was trying to think about how do we improve teaching about science? How do we improve the inquiry so that we can make progress on these questions?
Going back a little bit to the strictly science historical nature of geosciences. So this listener asks, to what extent do you think Peirce was influenced by the historical nature of the geophysical sciences, where past events may not be reproducible?
Right. So this is interesting. Very good. So I think the geosciences I find particularly exciting because they are a very interdisciplinary science, and they're not. Oftentimes they have been characterized as a science that's just a historical science. So you might think, what are the sciences that are historical sciences that are trying to tell the story of the past? And certainly an important part of the geosciences is, as a historical science, trying to reconstruct the 4.5 billion years of Earth's history, evolutionary history, and so forth. And that involves certain kind of limitations in that you can't always do these experiments and you can't sort of go back and check against this history. So that's one element of it. But then geosciences are also this very empirically lab-based science as well. And so if you think about geodesy today, they're doing measurements, experiments. If you think of radiometric dating, that all happens in a lab. So it's a very sort of methodologically omnivorous science in that it's not purely lab, it's not purely historical, but involves bringing many different methods together to make progress on these questions. And I think the geosciences are trying to deal with these vast spatial scales, the whole shape of the whole Earth, these vast temporal scales, the 4.5 billion years of Earth's history. And as such, they recognize how important it is that in this Earth system, we have biological, climate, rock, we have all of these different, we have social systems with human beings these days interfering with our system in various ways. To understand, we need to bring all of these disciplines together. We need to bring all of these different methodological tools to the table. And so I think that is part of something that has been recognized in the geosciences for a long time. Its interdisciplinary nature, its multi-methodological nature, and so forth. And I think, we see Peirce recognizing that it's not merely a science of describing that history, but it's also a science that we might call nomothetic, that is trying to develop these generalizations, these laws, and develop this broader understanding as well. So I think the historical nature of the geosciences was important for him, as well as this interdisciplinary nature.
Right. We have time for one very short question and one very short answer, hopefully. Were there any contemporary applications of geodesy in Peirce time?
So I think he was really concerned with the basic scientific question of the figure of the Earth and the degree of polar plotting. He was also very concerned with how these gravity measurements could be used to start to infer things about the subsurface of the Earth. That's something I didn't get a chance to talk about, but the gravity measurements not only can be used to draw conclusions about the shape of the Earth, but they can also, these gravity measurements in variations in gravity, very minute variations in gravity, how they can tell us about what's below the surface of the Earth. And so Peirce very early on recognized the value of these pendulum measurements far beyond this sort of basic scientific question. For example, discovering where there's greater density, where there might be water, where there might be oil and gas, right? We can use these gravity measurements on the surface to come to understand what's below the surface of the Earth. And it can be used to give us seismic information, earthquakes, so forth. So these gravity measurements are something Peirce was very much thinking about in a practical way. He has an essay where he talks about the 6 different applications of gravity measurements beyond measuring the figure of the Earth. So he was very much concerned with the various practical applications and how, if the accuracy of these measurements could be improved, the pendulum measurements could be improved, they could open up whole new worlds of knowledge for us, such as the interior of the Earth, which we can't directly access except through these surface measurements. So thank you for that question.
Thank you, Alisa. Thank you for the wonderful presentation and the fascinating conversation. I also want to thank our audience for the terrific questions. I hope you'll be able to join us for other Radcliffe virtual programs. You can find out about future programs and watch videos of past events at radcliffe.harvard.edu. Thank you again for joining us today, and have a great rest of the day. Happy holidays. Bye-bye.